Hey kiddos, welcome back. Today we're going to talk about three basic states of matter. My guess is you've heard of most of what I'm going to talk about today. So let's just dive right into it. The three basic states of matter are the solid state, abbreviated with the lowercase s, the liquid state, abbreviated with the lowercase l, and the gaseous state, abbreviated with the lowercase g. Now what I want to do is I want to actually draw representations of these states of matter as if we could see them with the world's strongest microscope that doesn't exist. So let's try to draw these images. I'm going to draw three squares here, and underneath the first one we're going to put an S, and then the second an L, and the third a G. Now, if I could see some solid particles at the atomic or molecular level, I would see something really pretty cool, I think. They are very organized. They form what's called a crystalline lattice inside my container. They're very, very tightly packed with each other. They have a definite shape, and they certainly do not occupy the entire volume of their container. Liquids, on the other hand, are a little bit less organized. They don't have a definite shape. They end up taking the shape of their container. But if I could draw some liquid particles here, I might draw something like this. They're not quite as closely packed. As a result, they are essentially incompressible, but they're close enough together, or far enough apart, you can get a little bit of compression, but essentially we say that they're not compressible. But they're certainly not as organized as solids are. Gas particles, there's huge distances between them. They end up occupying the entire volume of their container. They take the shape of their container. They can flow easily past one another. In fact, let's start writing some of these properties down, should we? So for solids, let's start out by saying that they have a definite shape. They do not take the shape of their container. So a definite shape. If I were to put a rock inside of a jar, the rock doesn't change its shape to take the shape of the jar. The rock takes the shape of the rock that you put in there. It has a definite shape. Solids form crystal lattices, so they form crystals. Let's just write crystal lattice. It's a specific pattern for that type of solid. They cannot flow. Now, that doesn't mean solid particles don't move. They can vibrate back and forth, up and down, and sideways. They vibrate about a first fixed point, but they can't flow past one another within the solid. They have a fixed volume. They don't take the volume of their container. They have a specific volume, and no matter where you put them, they'll have that same volume. They are not compressible. They are so close to each other, we can't squish them any closer to each other than they already are. Now for liquids, let's see, do they have a definite shape? No, they don't. Liquids take the shape of their container. So I'm just going to put here, takes shape of the container. If I have some water and I pour it into a beaker, it takes the shape of that beaker. If I take it from that beaker and put it into a flask, see, a flask would look like this. It would then take the shape of that flask. If I take the liquid from that flask and pour it into a big test tube, it would take the shape of that test tube. So liquids are able to take the shape of their container. They don't form crystals. They can flow. So within the liquid particles can flow past one another. They still have a fixed volume. They don't occupy the entire volume of their container. They have a fixed volume. So if I have a beaker that might be able to hold 1 liter of liquid, and I only have a half of a liter of liquid in there, it doesn't expand to take up the entire volume of that container. It has a fixed volume, and I can move it from that container into another container, and it will still have the same volume of a half of a liter. And for all intents and purposes, liquid particles are so close together, they are not compressible. You could argue that a little bit, but we're going to say they are not compressible to any great extent in this class. How about gases? Do gases have a definite shape? No, they don't. They also take the shape of their container. So take shape of container. Of course, they can flow past one another. They take the volume of their container, so they don't have a fixed volume. So they occupy the entire volume of their container. And if you switch their container to a bigger container, it'll occupy the volume of that bigger container. They're not attracted to each other at all, so that they diffuse or they move throughout their container to occupy the entire volume of that container. And one interesting thing that's interesting about gases that's different than liquids and solids is that they are compressible to a great extent. You can push gas particles closer and closer and closer to each other. They are compressible. In fact, if you apply enough pressure to a gas, you can actually cause it to become a liquid. You can squish the particles so close to each other. Okay, the last thing I want to talk about in this video quickly is the change of state from a solid to a liquid to a gas and then backwards. If I were to try to take a solid and turn it into a liquid and then that liquid into a gas, you would see I would have to add heat or add energy. We call these processes endothermic. That means it requires heat from the surroundings. So I'm just going to put in quotation marks, we have to add heat to go from a solid to a liquid to a gas. What if we were to go backwards from a gas to a liquid to a solid? Well, if you're familiar with the law of conservation of energy, if we have to add heat to go in one direction, that means we would give off heat going in the opposite direction. So going from a gas to a liquid to a solid, we call these exothermic. They release heat to the surroundings. So I'm going to put in quotation marks here, release heat to change from a gas to a liquid to a solid. In fact, let's graph this quickly. On the bottom right-hand corner of your notes today, let's draw an axis. I have a y-axis and an x-axis. The x-axis we're going to label heat. And as we move to the right, we're adding more and more heat. The y-axis, let's call this one temperature. So we're going to start at a low temperature and we'll increase to a high temperature. And let's do this for water. All right, let's start at, just for fun, negative 25 degrees Celsius. So you pretend you filled up a beaker with water, stuck a thermometer in it, and then placed it in your freezer overnight. When you pulled it out the next day, the thermometer read negative 25, and you have frozen solid water. Now, as you begin to add heat to this beaker of frozen solid water, maybe you put it on a hot plate or your stovetop, or maybe over a Bunsen burner. To no one's surprise, the temperature of that frozen water begins to increase. But something interesting happens for water at 0 degrees Celsius. That's the melting point of water. And the water begins to melt. As it melts, the temperature does not change. It stays constant until all the water is melted. And then when that phase changes over, the liquid temperature can then begin to rise again. That continues to rise until, for water, it reaches 100 degrees Celsius, which is the normal boiling point of water. And at that point, the temperature doesn't rise any longer. It stays constant until all of that liquid has been converted into a gas. Once that has happened, the phase change is complete. The temperature of the vapor can rise. So, if you take a look here on my graph, from this point to this point, do you remember that the water was in the solid phase? And here on my graph, from here to here, do you remember what was happening at 0 degrees Celsius? The temperature wasn't changing, was it? Why not? Because it was going through a phase change. So we were going from the solid to the liquid phase. And then on this portion of my graph, didn't we have just the liquid phase? And then right here at this point, my liquid started to boil, didn't it? And the temperature didn't change again as it went through that phase change. So here, all the way to here, we have the liquid turning into a gas. And then finally at this point on up, the only phase that we have is the gaseous phase. So when we go to the right on this graph, remember when we add heat, we go to the right, that's going from a solid to a liquid to a gas. Now what if I had gone backwards? What if I started with water vapor at maybe, I don't know, 120 degrees Celsius and cooled it down? Wouldn't it be going in this direction then and giving off heat from here to here? Here the temperature wouldn't change until it was all liquefied. Then from here to here the temperature would drop. From here to here, right, the temperature wouldn't change until it was all frozen, and then it would go to whatever final temperature we took it at. So this graph illustrates the energy required or given off when water goes through a phase change. Okay, there's some cool demonstrations I have related to this, especially this one right here, where I boil water in a paper cup over a Bunsen burner. The cup doesn't burn, but the water boils. Sort of interesting. All right, that's good enough for today, kiddos. We're going to talk to you soon. Bye-bye.